Hello. In this video, we are going to talk about cylindrical coordinates. Now, in cylindrical coordinate system, a point is represented by an ordered triple r theta and z, where the pair r and theta are the polar coordinates for the projection of the point P on the xy plane, and z is the Cartesian coordinate. Now, let's look at this picture to understand better the cylindrical coordinates. So here is our point P in space. We take its projection onto the xy plane and call it P prime. Then we represent P prime in polar coordinates. So we measure the angle from positive side of the x-axis to the ray O P prime, and then it is theta, and then we measure the distance between the O and P prime, and that is r. Now z, it's the same z as in the Cartesian coordinate. Now, let's see the relation between cylindrical and Cartesian coordinates. Now, to convert a point from a cylindrical coordinate to Cartesian coordinates, we use the relations x equals r cosine theta, y equals r sine theta, and still z is the same z as in Cartesian coordinates. Now, remember that those expressions of x and y are the same as in polar coordinate system. Now, to convert from Cartesian coordinate system to cylindrical coordinate system, we use, again, the relations similar to the relations in polar coordinate system. R squared is still equal to x squared plus y squared, and tangent theta is equal to y over x, and z, it's still equal to z. In this exercise, we are given a point in cylindrical coordinates. The point P is 2, 5 pi over 6, and -1. And we'd like to find its Cartesian coordinates. So, we are going to use the first set of relations. So, x is equal to r cosine of theta, and r is 2, and theta is 5 pi over 6. So the value of x is equal to 2 times -√3 over 2. So the x coordinate is equal to -√3. Now for the y coordinate, we will use the relation y equals r sine theta. So it is 2 times sine 5 pi over 6, which is 2 times 1 over 2, which is equal to 1. So the y coordinate of the point is equal to 1. And the z coordinate, it is same in Cartesian and cylindrical coordinates, so it is still -1. So the point P in Cartesian coordinates is -√3, 1, and -1. In this exercise, we want to find the cylindrical coordinates of the point P, which is √3, -√3, and 1, given in Cartesian coordinates. So, to find the cylindrical coordinates, we are going to use the second set of relations. So r squared is equal to x squared plus y squared. So square of √3 plus square of -√3. And so r squared is equal to 6. So r is equal to plus or minus √6, but remember from the discussion of polar coordinates that we can always work with positive r. So we choose r to be √6. Then the other relation that we will use is tangent theta equals y over x. So y is -√3 and x is √3. So tangent theta is equal to -1. And the solutions of this trigonometric equation are 3 pi over 4 plus 2 pi n, or theta equals 7 pi over 4, so fourth quadrant, plus 2 pi n. Now, we are going to choose this as our solution. It's because, now, if you check the x and y coordinates of the point, it's positive x and negative y, which means that the projection of this point P onto the xy plane is in the fourth quadrant, because projection of P onto the xy plane is in the fourth quadrant. So we choose a solution in the fourth quadrant, and therefore the point P in cylindrical coordinates is root 6, that's for r. Now, I can choose 7 pi over 4, and the z coordinate is still the same as in Cartesian coordinates, so which is 1. In this exercise, we want to describe the surface whose equation in cylindrical coordinates is r equals 2. Now, in this equation, we don't see the theta and z. So this means theta and z are free variables. So let's have here our three-dimensional coordinate system. Now, theta is a free variable, means that we are allowed to do a full rotation on the xy plane. And z is a free variable, means that we are allowed to visit any level along the z-axis. And r equals 2 means that our distance to the origin is always 2. So all of this describes a cylinder along the z-axis with radius 2. And this is an infinite cylinder. So, infinite cylinder with radius 2. In this exercise, we want to describe the surface whose equation in cylindrical coordinates is theta equals pi over 4. In this equation, we don't see the r and the z. It means that they are free variables. So, here is our three-dimensional coordinate system. And we start the sketching with the sketch of this equation on the xy plane. In other words, we are going to sketch its trace on the xy plane, and that is a line where the angle between the positive side of the x-axis and this line is equal to pi over 4. And then z is a free variable, means that we can have this line along any level on the z-axis. So this here, it's going to be this equation, it's going to represent a plane. Hello. In this video, we are going to talk about triple integrals in cylindrical coordinates. Suppose that we'd like to calculate our triple integral over a solid E that lies between the surfaces z equals u1xy and z equals u2xy. To understand better our solid E, let's have a look at this picture. So, this blue object is our solid E. Now, we assume that the bottom of this solid lies on the surface z equals u1xy, and the top of the surface lies on the surface z equals u2xy. We also suppose that the solid E, the projection of solid E onto the xy plane can be easily described in polar coordinates. So, if we look again our picture, so here is the projection of our solid onto the xy plane, and I can describe this easily in polar coordinates where theta changes between alpha and beta, and the r's change from this polar curve to this polar curve. So here, this point is on the polar curve r equals h1 theta, and this point is on the polar curve r equals h2 theta. Then, if our solid have such a description, the triple integral over the solid E of f is equal to the following triple integral. The first integral from alpha to beta, it is with respect to d theta. The second integral is from h1 theta to h2 theta, which is with respect to r. And then the third integral, it is from u1 r cosine and r sine to u2 r cosine r sine, which is with respect to z. Now, if you have noticed, we have changed the x and y, the Cartesian coordinates, into cylindrical coordinates of the function f of r cosine, r sine, and z. Again, here in the function, we change the Cartesian coordinates into cylindrical coordinates, and then times r, dz, dr, d theta. In this exercise, we want to evaluate the triple integral of the function x squared plus y squared, where the boundaries of z are from 0 to x, the boundaries of x are from 0 to root 1 minus y squared, and the boundaries of y are from 0 to 1. Now, before we start integrating, let's understand better the solid E over which this triple integral is going to be evaluated. So our solid E, it's the collection of points x, y, z, where x's are between 0 to and root 1 minus y squared, and the y's are between 0 to 1, and the z's are between 0 and x. Okay, now let's also check the projection of this solid on the xy plane. So let's call it D. It's going to be collection of points xy, where x's are between 0 and root 1 minus y squared, and the y's are between 0 and 1. So the first thing that I observe in this description of the projection is that all y's and all x's are positive. So this means our projection is in the first quadrant. And I also recognize that this equation, x equals root 1 minus x squared, it is a circle with radius 1. So our region D, it's going to be quarter of a circle with radius 1 in the first quadrant. And since D, which is the projection of our solid E onto the xy plane, it's a circular region, we can express this better in polar coordinates. So D in polar coordinates, it's going to be a collection of points r and theta. Okay, now to describe this region, I have to rotate from the positive side of the x-axis till the positive side of the y-axis, which means that the thetas are between 0 and pi over 2. And then, to find the interval of r, I use this auxiliary ray. So the r's change between these 2 points. So, and this point is the origin, this point is on the circle. So I need the equation of this circle in polar coordinates. So here is its Cartesian equation, and r equals 1 is its polar equation, and the r's are changing between 0 and 1. Now, since the projection of the solid E is better described in polar coordinates, I say better described because check the boundaries of the polar coordinates, theta and r, they are all constants. So this description is simpler than this description in Cartesian coordinates. And because of this, we are going to use cylindrical coordinates to evaluate this triple integral. Now, to obtain the same integral, or to rewrite the same triple integral in cylindrical coordinates, I am going to express the boundaries of this triple integral in cylindrical coordinates first. Now, I have expressed already the boundaries of r and theta in polar coordinates. Now, we need to express the boundaries of z also in cylindrical coordinates. So, z is equal to x in Cartesian coordinates, and in polar coordinates, z is equal to r cosine theta, and z is equal to 0 in Cartesian coordinates, it's still equal to 0 in cylindrical coordinates. And so here are our 3 integrals. The first one, it's with respect to theta, so its boundaries are from 0 to pi over 2. The second one is from 0 to 1 with respect to r. And the third one, it's going to be, for z, will be from 0 to r cosine theta. Okay. Then next, I need to express the function in terms of the function in the cylindrical coordinates. So x squared plus y squared in cylindrical coordinates, it is equal to r squared. And then I will have r dz dr d theta. So now we can start integrating. The first integral is with respect to z. So I will have r cubed z evaluated from r cosine theta to theta. Then later we will integrate with respect to r and theta. So this here gives us r cubed times r cosine theta. Let me rewrite this one more time. 0 to pi over 2, then 0 to 1, r to the power 4 cosine theta dr d theta. Now, this double integral, it is an iterated double integral in polar coordinates. It is iterated because the boundaries of r are, as you see, 0 and 1, and they are independent from the variable theta. So, to evaluate this double integral, I can separate the variables. So I will have one integral with respect to theta, and times the second integral, which is integral of r to the power 4 with respect to r. And I evaluate each one of those integrals. So integral of cosine is sine of theta, evaluated from pi over 2 to 0. And then times integral of r to the power 4, it's r to the power 5 over 5, evaluated from 0 to 1. So sine at pi over 2 is 1 times 1 over 5. So the value of this integral, this triple integral, is 1 over 5. In this exercise, we want to find the volume of the solid that lies between the paraboloid z equals x squared plus y squared and the sphere x squared plus y squared plus z squared is equal to 2. So, to understand this solid better, let's sketch this paraboloid and the sphere. So, here is the sketch of the sphere with radius root 3, root 2, and here is the sketch of the paraboloid. Now, the solid mentioned in the question, it's this red region. So, let's describe it in Cartesian coordinates. So, it's the collection of points x, y, z where the following conditions are satisfied. So, what I see from the picture is that all the z's are above the paraboloid. So, the z's must be greater than or equal to x squared plus y squared. And from the top, this solid is bounded by the sphere. So, all the z's should be less than 2 minus x squared plus y squared inside the parentheses. And that would be our description of the solid E in Cartesian coordinates. Now, we want to calculate the volume of this solid, and it will be the triple integral over this solid of the constant function 1. Now, to decide what kind of coordinate system we should use to evaluate this triple integral, we have to check the projection of the solid E onto the xy plane. And to understand the projection, first of all, we should look at the intersection. So, which I mark here in green. So, we are going to put the paraboloid equation inside the sphere equation. X squared plus y squared is equal to z. So, I have z plus z squared is equal to 2. And if you solve this quadratic equation, first you have to factor it. And then you find the values of z. Now, as you see, z equals 2 cannot be an intersection, as you can see it from the picture. So, the intersection is z equals 1, the one that I have marked in green in this picture, and this is the plane on which the intersection is happening. So, the intersection, it's the circle x squared plus y squared equals 1 on the plane z equals 1. Now, the projection of the solid onto the xy plane is the disk with radius 1. So let's sketch it. And we can describe this disk easily in the polar coordinates, where thetas are changing between 0 and 2 pi, and the radius is changing from 0 to 1. And since the projection is better described in cylindrical coordinates, we can express this volume in cylindrical coordinates as follows. So the first integral is from 0 to 2 pi. Second integral, it's with respect to r, so the boundaries are from 0 to 1. And the third integral is going to be with respect to z, so I have to express the boundaries of z in cylindrical coordinates. Now, if you check the definition of the solid, you are going to see the boundaries of z in Cartesian coordinates. So we change them into cylindrical coordinates. So let's do them here. X squared plus y squared. In cylindrical coordinates, it's going to be r squared. And root 2 minus x squared minus y squared in cylindrical will be z equals 2 minus r squared. So we use those boundaries, 2 minus r squared. So function is still 1, and dv in cylindrical coordinates is r dz dr d theta. Okay, so the volume is ready. It's expressed in cylindrical coordinates, and we can start integrating. First, with respect to z, and then we will substitute r squared and 2 minus r squared. We will have 0 to 2 pi, 0 to 1, r root 2 minus r squared minus r cubed dr d theta. Now, what we observe here is that this is an iterated double integral in polar coordinates. It's because the boundaries of r are independent from the variable theta. So, to evaluate this double integral, we can separate the variable r from variable theta. We have one integral from 0 to 2 pi d theta times the other integral 0 to 1 of r 2 minus r squared. And to evaluate with respect to r, I'm going to separate it into two integrals. So first one is r root 2 minus r squared, and the other one is r cubed. Okay, so the integral with respect to theta, it's going to give us 2 pi. To evaluate the first integral in r, I have to do substitution. So for this integral, we do substitution. Let's say we are going to call u 2 minus r squared. So therefore du will be negative 2 r dr. Now let's also change the boundaries. If r is equal to 0, then u will be 2. And if r is equal to 1, then u is going to be 1. So using u, our first integral in r, it's going to be integral from 2 to 1. So r dr from this substitution will be du over negative 2. And we are going to have root of u, which is u to the power 1 over 2. Then I don't need to do any substitution for the second integral. So we have the first integral, it's 1 over 2 times integral of u to the power 1 over 2, it's 2 over 3, u to the power 3 over 2, evaluated from 1 to 2, minus integral of r cubed, it is r to the power 4 over 4, evaluated from 0 to 1. Now, we substitute the boundaries. So, here we have negative 1 over 3, 1 minus 2 to the power 3 over 2, and then minus 1 over 4. Now, the rest is simplification. It's 2 pi. 2 to the power 3 over 2 is bigger than 1. So, this is going to leave it as 2 over 3 root 2. And then minus 1 over 3 and minus 1 over 4. And this simplifies to 2 pi 2 root 2 over 3 minus 7 over 12.